All right, let's take a look at our lesson on inverse functions. First, let's look at the definition of an inverse function. And in the definition, they talk about something that you may not be familiar with, a one-to-one function. Okay, one-to-one. So before we continue with the definition, just because I'm not sure, some people may not know what a one-to-one function is. So a one-to-one, let's just skip here for just a moment. A one-to-one, a function is one-to-one if and only if, this is called the horizontal line test. So let me give you an example. So let's say we look at this function. We know that's a parabola. And if we can draw a horizontal line through it and it touches the function or crosses the function more than once, it is not one-to-one. So this function is not one-to-one. An example of one that is one-to-one, let's just look at an example, this function. This function is one-to-one because I can draw horizontal lines anywhere and they only intersect the function one time. So this one is one-to-one. All right, so let's go back to the definition. So it says f has to be a one-to-one function, and if it is not a one-to-one function, we do have some techniques where we could restrict the domain to force it to be a one-to-one function, and we'll look at an example like that. So either f is a one-to-one function, or we have forced it to be a one-to-one function by restricting its domain. Then the inverse of the function, now I do want you to look at this notation right here. This notation for many students is very confusing. That little -1 looks like an exponent, but it is not an exponent. It is an indication of inverse. So just a heads up, that does not mean f of -1 is -1 is an exponent. It signifies that it's inverse of f. And so what we do to find the inverse, or they're saying this is the definition of the inverse, is notice that the x's and the y's have been flipped. Okay, that is the huge significance here, is that the x and the y has been flipped. And we're going to find inverse functions using that technique in just a moment. And so, how do we find the inverse of a one-to-one function? Well, first of all, we'd have our function, our regular function. And this step 2, solve it for x in terms of y if possible, that is a fine step. Usually here's what I do. Okay, so we have our function, we switch the x and the y, and then we solve for y. So this would be step 2, this would be step 3. So we switch the x and the y, and we solve for y. Okay, and we'll do some examples of that. So how could you tell if a function is, an inverse of another? Is there a way to do that? And there is. This is an algebraic technique. Okay, in this algebraic technique, if we do a composite, remember our lesson on composite functions? If we do the inverse of f of x and get x once we have everything simplified, or we do the reverse, we do f of f-1 of x, we do the composite and get x, then they are inverses. The equations are inverses of each other. That's the algebraic way to do it. The graphing way, would be graphical. The graphical way to determine if a function is an inverse of another function would be to look at the graphs and determine if they are reflected over the line y equals x. As we can see in this example right here, we see this function f has been reflected over the line y equals x perfectly. So that's the graphical way to determine. See how, let's see how that was the x and that was the y, and in the reverse, that, the y became the x and the x became the y. They've been flipped. That's how the points work. And those points are also reflected over the line y equals x. All right, this would be the line of symmetry for inverse functions. Gosh, I can't write. Okay. All right, well, let's do some examples now that we hopefully have kind of the concept, at least an intro to the concept. Let's apply this. Let's do some examples. So let's focus on this example. They want us to list 5 significant points, and just so nicely they are listed for us. So let's just do it in T-chart form. So this point right here, and this is kind of hard to see, isn't it? This is the x-axis, excuse me, the y-axis. Let me just do it in a different color. This is the y-axis. It didn't come out very well on the copy, but that's the y-axis. Okay. So the first point is -3, 3, this one right here. Then we have -2, -1. Then we have -1, 2. Then 1, 1, and 1, 2, 3, 3, 4. Okay, so check. We listed the points that they told us to list, the 5 significant points. Now they want to know what are the corresponding significant points for its inverse. Well, let's write those points. I'm just going to switch the x and the y around, right? Isn't that what an inverse is? Is where you switch the x and the y? So that's what I'm doing. I'm taking these points up here and I'm reversing. The x became the y and the y became the x. Okay, and now, so we have those corresponding significant points. Now they want us to sketch those points. Let's sketch that in pink. So I've got 1, 2, 3, 1, 2, 3. Then we've got -1, -2. Oops, -1, I did 1, -1, -2. Silly Billy. Then we have, what do we have? 2, -1. Then we have 1, 1. And then 4, 3, 1, 2, 3, 4, 1, 2. Okay, let's look at so this would be the line y equals x, which is our line of symmetry. And okay, good. That looks, we can tell graphically that that's a reflection. So we did graph it, looks great. Now the question is it a function? Now how do we know if it's a function? Remember, we would know if it's a function does it, for a function, now it's not talking about one-to-one, it's talking about an actual function. Maybe you remember from Algebra 1 how to tell if something is a function or not. Remember that? It's called the vertical line test. How you would, if you draw a vertical line and it goes through the function more than once, which it does here, it's not a function. So the inverse is not a function. All right, so it is not a function. Okay. So let's move on to this example over here. They want us to determine the inverse functions for each of the following. So what we're going to do is we're going to go through these steps. Remember these steps right here? We have our function. We're going to switch the x and the y, and then we're going to solve for y. That's the procedure we're going to do here. So recall, maybe you do or maybe you don't recall, but this means y. That means y. So we're going to switch the x and the y. So the y becomes the x, and the x becomes the y. And then we're going to solve for y. So I'm going to move the 4 over, and then I'm going to divide by 2. So I can divide each, so I divided each one of them by 2. I can divide them separately, or I could write it like this. Either of these is acceptable. Either of them is fine. Now, it's inverse, so typically what we would do is instead of writing y, we would write f negative 1 of x. So instead of writing y, we're going to write f negative 1 of x. Okay, now let's do our other one, number 2. Notice that they have a domain restriction. This is a parabola. Let's think about parabolas in general. Parabolas are not one-to-one functions, so as I was talking a little bit ago, if a function is not one-to-one, we can force it to be one-to-one by restricting the domain. And so basically that's what they've done here, is they've restricted the domain. They have said that x can only be 0 or greater. It cannot be negative. In the case of this parabola, y equals x squared, if I did something like x is greater than or equal to 0, what would happen is I would just have this part right here. I wouldn't have the other part. And this part by itself does pass the horizontal line test and is one-to-one. So that's the fix. The fix for functions that are not one-to-one is to restrict the domain, which was done here on number 2. Okay, so great. We've got that. That looks good. We don't have to worry about restricting it. They did that for us. So let's just go through the procedure. Remember that this is the y. We're going to switch the x and the y, so I have x equals negative 3y squared plus 5. Now my job is to solve for y, so I move the 5 over. I divide by negative 3. And then I square root both sides. So y is plus or minus the square root of x minus 5 over negative 3. Okay, now that gives us 2 pieces, right? A plus and a minus piece. But we need to, we need to pay attention to this, and we need to choose. We need to choose which one of those we're going to use, because we need to have the x is greater than or equal to 0 part is the part that we need to have. So let's think about this right here. Would look like that. X greater than or equal to 0. It's going to be the x greater than or equal to 0. Yeah, we want the y's. So in this case, if x is always positive, so with the y's, it's the inverse, right? The inverse, we want y to always be positive. Remember, because we are switching the x and the y. Their domain switch, everything switches. So if x is always positive in the original, we want y to always be positive in the inverse. So we're going to choose the positive one. So x minus 5 over negative 3 would be our inverse. And we could do that g negative 1 of x would be our inverse. All right, great. Let's look at our last example. On our last example, we're given two functions and we're just asked to verify if they're inverses of each other. You know, that goes with, let me just remind you, we're going to do this algebraically. We're going to practice this algebraic technique. We're going to do a composite function. That's what we're going to do. And then see if it simplifies to be just x. All right, so let's check that out. So let's do f of g of x. So I'm going to open up where the x is, and I'm going to insert the cubed root of x plus 7 cubed minus 7. Okay. So the cubed root and the cubed cancel each other out. So that's going to be x plus 7 minus 7, which is x. So check. Yes, they are inverses of each other. Just for fun, let's do the other one, g of f of x. So I'm going to take the function g, going to insert in place of x, x cubed minus 7. Okay, so I have the cubed root of x cubed minus 7 plus 7. It's the cubed root of x cubed, which simplifies to be x. So check, it worked both ways. All right.